Okay, so the next thing we're going to talk about is just this really interesting phenomenon called resonance. Okay, but in order to do that, we have to really make sure we understand oscillations. And so let's talk about, we've talked a lot about spring and mass systems. Okay, and the thing that's really interesting here is that based on the mass of the system and the spring constant, how stiff the spring is, we can predict how fast it will oscillate, like what the period of oscillation would be. And this is true no matter what the amplitude is, okay? No matter what planet it's on, all right? And so what this comes down to is this is kind of a property of this system, part of the system's physical properties. And it's something that doesn't change unless you were to alter the materials involved, if you were to add or remove mass or to change the spring somehow. And so this system otherwise is like this forever. And as long as, if you ever make it oscillate, this is the speed at which it oscillates, okay? And the only way we can affect those oscillations is either to add energy or to take energy away from them. And we already saw earlier what it looks like when you take energy away. But it turns out that you can also add energy to an oscillation, okay? If this system is oscillating, and every time it comes here, I push it at just the right time, then I can actually increase the energy of this system, okay? If I'm increasing the energy, remember the total energy of the system is 1/2 k x sub m squared. I'm not changing k, so that means I'm changing this, which means the amplitude of those oscillations will get bigger and bigger and bigger. Okay, the best way that you can picture this is somebody on a swing. Okay, so if you have somebody on a swing and they're swinging forward and you push them every time they come back, then you're timing your pushes just right to increase the energy of these oscillations so they swing higher and higher. And when you do that, what you're doing is you're matching the resonant frequency of this system. Okay, anytime there's an oscillating system, if you match its frequency, you can add energy to those oscillations. And this has some very powerful consequences, some that have significant effects to us, some of them that are just fundamental to everyday life. So this is what's the reason why we have musical instruments, okay? You can create music by causing something to resonate at its natural frequency, okay? And that's done by forcing air, generally through most musical instruments, by forcing air through it, causing them to vibrate at those natural frequencies. Now, if you could imagine that materials are made up of masses and springs bonded together, okay, they're not necessarily masses and springs, but they are masses that are connected through some type of bond, okay, and this bond is something that can move, it's not fixed. And so if you have a collection of masses that are attached with something similar to springs, then they can oscillate. And generally they're all oscillating on their own, just kind of bouncing around. But if you were to apply a push at just the right time, you get them all oscillating together and cause them to oscillate. And cause them to oscillate through resonance, and these oscillations can become very large and very powerful. And so I'm going to show you a couple examples of this.
Clearly time for some physics fun. What I've got set up here is a vibration generator. So the pin here will move up and down. I have a spring, and that's a spring with a K of about 30. And then I have a 100-gram mass, and I have a second spring attached to a clamp stand that's out of shot. So it's a dead simple experiment to do. We have the signal generator at the back here, and at the moment I've turned down the amplitude. So I'm going to turn up the amplitude, which is hidden, and we're going to put it on maximum, and hopefully you can clearly see that this pin now is vibrating at a frequency of 2.06 Hertz. Now let's see what happens if we dial down the frequency. We're now going at 1 Hertz, well, nearly a Hertz there, 1 Hertz frequency. So up and down, okay. Let's go up a little bit. We'll go slowly so you can clearly see, getting a bit more motion with that mass. And I've done a scale on the back here, and this is in centimetres, so it's every 2 centimetres. I did a bit of a line at the mid value. Now it's not perfect because I'm on a bit of an angle, but it's not really designed to do an accurate display. We're just looking for an overall effect. So 2 Hertz, pretty much the same thing is happening. So let's go up a little bit more. There we go. 2.5. It seems to have died off now. There's not a lot happening. 2.7, 2.8, 3 Hertz. Interesting. Wow. 3.2, 3.3. Crikey. The amplitude is massive. Looking at least 14 centimetres. Well, let's just go up a little bit more. 4. Oh. Oh dear, it's died off. 4.4. 5. 5. Oh, it's gone. That effect has gone. Let's go back.
Okay, so hopefully you noticed here that there was a certain frequency that causes the amplitude of those oscillations to increase significantly, and that there was other frequencies around there, and as you got further and further away, that just kind of caused it to slow down and didn't really have much effect on it. You might have even noticed that there was a certain frequency, about half of that resonant frequency, that also caused it to start to oscillate when he showed it at about maybe about 1.15-ish. Okay, you see it starting to oscillate a little bit more there.
Getting a bit more motion with that mass.
So that would be kind of like if you were pushing someone on a swing, but only pushed it every other time that they came back. And so this was a frequency that also kind of caused some oscillations, but not with the amount of strength that you did at that natural resonant frequency right here. This is the natural frequency that the system wants to vibrate at, and so when you push it at that frequency, it causes those vibrations to amplify. So this is another example of resonance where by timing the pushes, they're able to cause this really shaky bridge to amplify its oscillations based on its natural oscillating frequency. Okay, and you can see that those oscillations get kind of bigger and bigger. Okay, and this is another example of resonance. This happens because they push and jump at the right times to make it oscillate. Okay, and then here's another visual there. Yeah, they actually here can make it like twist. There's a twisting example. I think, let's see. Here you can they make it oscillate side to side. Okay. So the key here though is that this bridge has kind of this natural frequency based on its shape that it wants to oscillate at, and it is really already oscillating at, and with very low energy vibrations. And as they come and jump on it, they add energy to these vibrations. Okay, and this is a really important concept too with designing buildings, because if you have a building that's designed a certain way and the natural frequency of the building is similar to that of an earthquake, then you can have buildings that will just shake themselves to pieces in an earthquake. So you've probably heard of people singing and breaking a wine glass. This is another example of resonance. It would be really difficult to break a wine glass by singing at it, but if you can create the right pitch and sing it with the right volume, you can cause the natural frequency of this glass. You can push it at that frequency and cause it to start vibrating at bigger and bigger amplitudes to the point where the structure of the glass would actually fall apart.
Oh, this is amazing. What felt like the whole goblet vibrating is actually the rim bending back and forth, 337 times a second, the same rate as the sound waves. If I draw in the sound waves, you can see what's happening. One wave comes out of the speaker and pushes the side of the wine glass. The glass bounces back just when another sound wave pushes it again. If the timing or frequency of the sound waves is exactly right, the motion will build until the glass breaks.
Okay, so again, that was another example of resonance, okay, where the push was at the same frequency of the natural vibrations of the material and caused those vibrations to amplify to the point where in this case, where the object broke, okay? But there's just some really cool demonstrations that you can do with resonance, and we'll try to do a few in class.